To accomplish these goals in an efficient and cost-effective manner, numerous factors needed to be addressed while planning the purchase of a heat treating system. These factors can be broken down into two categories: fundamentals and system performance considerations. The fundamentals include energy conversion, humidity, and air circulation. These areas should be covered thoroughly with potential equipment suppliers. Energy conversion has to do with converting a fuel into heat energy. Selecting of the fuel type will usually depend on local availability and cost per BTU, which plays a significant role in determining the cost of heat treating every board or pallet processed. Heat exchangers, direct fire burners, and boilers are standard devices for converting fuel into the heat energy needed to heat kilns and heat treating chambers. Moist air heats faster than dry air, so maintaining a high humidity condition throughout the heat treatment process reduces cycle time, lowers fuel consumption, and minimizes degrade problems. A high humidity condition also minimizes the risk of wood shrinkage, checking, splitting, cupping, honeycombing, and other degrade problems. Hot air traveling at high velocity throughout the chamber heats wood faster and more evenly, generating more uniform treatment and shorter cycle times. The optimum cubic feet per minute of air circulation is a function of the BTU capacity of the heating unit, the volume of material being treated, and the design of the treatment chamber. When it comes to investing in heat treating equipment, the best approach to making the right buying decision is to ask all the right questions to equipment suppliers, experienced operators of heat treating systems, and certifying agencies up front. The following issues should be discussed before a buying decision is made. Oversights in the planning stage can create problems and higher operating costs for years to come. Realistic production needs should take into consideration the volume of product that needs to be treated per day, week, or month, the type and size range of the products to be processed, annual climate conditions, and a reasonable allowance for growth. These issues have a direct effect on sizing the chamber, energy and air circulation system design, material handling requirements, and much more. Chamber design significantly affects three key performance areas: airflow, production capacity, and material handling. Chamber design plays an important role in facilitating smoother flow of high-velocity air uniformly throughout the entire charge, which translates into faster heat-up and processing time, more consistency in the heat-treated products, and lower operating costs. Chamber size controls the volume of material that can be processed per charge. Chambers that may handle GMA pallets very efficiently may prove to be very inadequate to process other size pallets or materials that also need to be processed. Chamber design directly affects the time required to load and unload every charge, which is a very important issue. The faster the chamber can be loaded and unloaded, the more cycles that can be run per day. Chambers that allow multiple forklifts to operate simultaneously speed up the material handling process. Energy consumption will include both the cost of the selected fuel type and the electricity required to operate the overall system. Once the production requirements have been determined and the system sized, a reasonable estimate of the cost of the total energy required per treating cycle should be established. Local environmental regulations should be reviewed relative to the energy source selected. Currently, two methods for controlling the heat treating sterilization process are recognized by various certifying agencies: the time and probe control methods. The time control method involves raising the chamber temperature to between 160 degrees Fahrenheit to 180 degrees Fahrenheit and keeping the load in this temperature range for a minimum of 3 hours. A temperature control with a recorder is usually used to generate the paper record of the treatment cycle that the certifying agency requires. Variables to this method may be imposed according to charts that consider species, moisture content, wood temperature, and other factors that would determine required cycle times. This approach can require longer than necessary cycle times, consumes more fuel, and is not acceptable to some certifying agencies. The second approach is called the probe method, which uses a thermocouple device called a probe to accurately track the temperature at the core of the wood during treatment cycles. This method allows the prescribed 30-minute heat treating cycle to automatically begin as soon as the core reaches 133 degrees Fahrenheit, which translates into shorter cycle times and less fuel consumption than the 160 degree Fahrenheit to 180 degree Fahrenheit for 3-hour time method approach. A PLC is used to control the operations, and a standard printer generates the final report after each heat treating cycle. The certifying agency hired will determine the number and placement of probes required. Loads are normally cooled down to a temperature safe for workers before the chamber is unloaded. The faster the cool down period, the less wood drying and degrade that occurs, and the faster the next cycle can begin. Cool down can occur by manually opening doors and vents, which requires workers to stay on top of the operation by opening vents automatically or letting the closed chamber sit long enough to cool down. In heat treating, drying poses several issues. Removing moisture from wood requires BTUs, which costs money. Drying wood can cause splitting, cupping, twisting, and other degrade problems, as well as cause wood nailed together to produce pallets, boxes, and other packaging products to split. But for wood packaging products that will carry food, pharmaceuticals, or other products that cannot be exposed to mold and stain, either surface drying or reducing overall moisture content to below 20% may be required. If drying is going to be required, then the system should be equipped with this capability. Besides its effect on retaining heat energy to speed up processing cycles and reducing fuel consumption, insulation plays a vital role in reducing condensation inside the chamber, which is corrosive by nature. A minimum of an R20 insulation helps to reduce condensation, while an R30 would provide even better results. In regions that experience very cold temperatures, insulation becomes an even more important factor. Considering the time and energy consumption required to heat up frozen wood in a chamber exposed to sub-zero temperatures, installing a chamber inside of a heated building and having a thawing cycle programmed into the control system should be considered. Loading and unloading requirements, the cycles that need to be accomplished per day, processing that will have to occur after work hours, and other issues that affect when and how many workers will be required to meet production needs, labor availability, and overtime pay, all should be considered in deciding how much automation should be included with the heat treating system. When a system shares a heat source, as with a plant boiler, the chamber may be loaded and ready for processing, but the heat energy required to run the ready load might not be available at the time, reducing the overall output capacity of the heat treating system. Material handling costs time and money. Strategically positioning the heat treating chamber convenient to both the production and the truck loading areas reduces material handling costs. Stacking plays an important role by achieving faster processing cycles and more consistency in the treatment process. Since improperly stacked material interrupts airflow and uniform circulation throughout the chamber. Since hot, moisture-laden air can produce a corrosive acidic condensation on the inside surface of the chamber, only corrosion-resistant materials should be used in the interior of the structure to reduce long-term maintenance expenditures. All electric motors that will be exposed to the hot and humid environment inside the chamber should be rated for kiln duty service to minimize potential motor problems. Since training can sometimes cost thousands of dollars, it is wise to know the cost up front if it is not included with the equipment purchase. Operators of the same system being considered for purchase can provide valuable details about its performance track record, operating costs, and maintenance requirements. Warranties can vary between equipment suppliers. It is wise to establish the length of the warranty and exactly what parts and labor are covered within that time period. Where the system is manufactured is another valuable piece of information. When it comes time for parts and service, the closer the supplier is, the faster and the less expensive service assistance will be.